All right, in this video, we're going to start notes 2 of Calc AB, and this is about the chain rule. So the chain rule is something that maybe if you've been following my videos, you probably felt like this rule is a long time coming. This is going to save us a lot of time when we're finding derivatives of some weird things. So it's basically the last of the rules. There's kind of another one that you sort of learned, but it's not actually a different rule. It's actually just the chain rule. But so we have a lot of stuff that we need to know. Basically, what we're going to try to find is we're going to try to find the derivative of a composition. So this is what we're starting with. And we're going to use the limit definition, right? So the limit definition of the derivative tells us that if y equals f of g of x, then dy dx should be, right? So it's like if that were h of x, right? No, let's say, I don't know, q of x. I don't know. It'd be q of x plus h minus q of x all over h. Right? So we have f of g of x plus h. Every x becomes an x plus h. F of g of x plus h minus f of g of x all over h. And the limit as h approaches 0. So we're going to do a proof of this. The proof, not particularly enlightening. But, before we start using it, I guess we should see a proof. So let's do it. So there are two kind of like insane things that we're going to do in the middle of this proof. And one of them is that we're going to multiply what we have by g of x plus h minus g of x over g of x plus h minus g of x. Very, very, very clever form of 1. And then the other thing we're going to do is eventually we're going to let g of x plus h minus g of x equal k. So like it's that weird form of 1 again. Well, it's the numerator or denominator of that weird form of 1. We're going to let that equal k. You'll potentially see why we're going to do that. So let's start off. So keep in mind we're starting with y equals f of g of x. All right, so if that's the case, dy dx will be the limit as h approaches 0 of, so it's f of g of, every x becomes x plus h here, x plus h minus f of g of x, and then all over h. Okay, so you look at that and you're like, there's nothing that I can do, because there's nothing you can really do there. But the thing you can do is this first weird thing. What if we multiply the top and the bottom by that? So I'm going to go ahead and put it in parentheses and then maybe change this up. So I'm going to multiply by g of x plus h minus g of x over g of x plus h minus g of x. Okay, and then I guess that parentheses should probably be in black. You got to match your colors. Okay. And as I said, I do not find this particularly illuminating. Like, you could go through life without seeing a proof of the chain rule and use the chain rule plenty well. In fact, I would say by the end of the year, maybe like almost 100% of my students have forgotten the proof of the chain rule, but they are amazing at chain ruling. So the next thing we're going to do, and it's kind of weird, is we are going to swap denominators. So we're just going to switch them. So I'm going to write basically the same thing again. So it's a quantity f of g of x plus h minus f of g of x over, now instead of writing h in this denominator, I'm going to write the other. So you're allowed to do that. You're allowed to just rearrange your denominators when it's multiplication. So g of x plus h minus g of x, and then times g of x plus h minus g of x over h. Okay. Feels like we didn't really do anything, but we kind of did, because that right-hand part of my fraction, so this part, if I take the limit as h approaches 0 of that, that's just g prime of x. So that's actually done. So that's really useful. So I'm actually I'm gonna do that. I'm gonna say, so this is the limit as h approaches 0 of this first part, which we'll worry about when we need to worry about it, which is soon, but not immediate, over g of x plus h minus g of x, and then times the limit as h approaches 0. So we're allowed to do this provided that both limits exist. So I always think that's kind of a backwards rule, because we don't know if we're allowed to do it until we try to do it, and it works or doesn't. And if it works, you were allowed to do it, and if it doesn't work, you weren't allowed to do it, so go back and undo it. Weird. All right, so this thing is g prime, so this is done. Okay, that's good. That's reassuring. So that's just g prime. So I'm going to write it again. So much writing f of g of x plus h minus f of g of x over g of x plus h minus g of x. Okay, and then times g prime of x, because that limit is g prime of x. That part's done. We don't have to worry about it anymore, and that's good. I'm going to do a space check here. I think I have enough space. Okay. So now, what do we do with this other limit? Well, I kind of told you what to do with it. I said that there's this weird thing we can do where we decide to let k equal this. So I'm going to say over here, let k equal g of x plus h minus g of x. All right, if I do that, then when h approaches 0, so if I let, so as h approaches 0, g of x plus h minus g of x approaches 0, which means as h approaches 0, k approaches 0. Okay, so that's one thing. As h approaches 0, k approaches 0. That's one thing that we need, so I'm actually going to highlight that. So as h approaches 0, k approaches 0. That's one fact. Another fact that we can use, because I have this g of x plus h that's like kind of embedded here, and that's kind of a problem for me. What I'm going to do is I'm going to take this and I'm going to solve it for g of x plus h. So also g of x plus h is equal to g of x plus k, right? Just add g of x to both sides up there. So this is a second useful thing that we've gotten out of this. Okay, so now where are we going with this? I'm going to make all my substitutions. So this becomes the limit not as h approaches 0 anymore. Now it's going to be the limit as k approaches 0. Limit as k approaches 0 of, so it's going to be f of, well, g of x plus h, according to the highlighted thing, is g of x plus k. G of x plus k minus f of g of x over g of x plus h minus g of x is actually k by definition. That's what we did. And then times g prime of x. Okay, look at this, right? This is essentially, I'm trying to find a good color here. This is essentially, if I'm going to highlight my g of x's, this is just f of, the limit is, as you could turn your k's back into h's if you want at this point. It's the limit is k approaches 0 of f of a plus k minus f of a over k. That's actually f prime of whatever a is, and a is g of x. So this is the limit definition of the derivative again. This is the derivative of f evaluated at g of x, and times g prime of x. This is the derivative. Let me move this a little bit and do this. This is the derivative with respect to x of f of g of x. This is the chain rule. So this is, you're going to use this like every time you take a derivative, pretty much. Not really, but like kind of. This is the chain rule. And you basically just need to practice it a million times. But it's, the derivative of composition is f prime of g of x times g prime of x. It's the easiest way to say it. So here are some of the ways that you'll see it written, right? So this one, the first one here is the one that we just ended up with, f prime of g of x, g prime of x. You'll often see it written as the derivative with respect to x of f of u. So in this notation, u is really u of x. It's a function of x. So it's f prime of u times du. Du just means find the derivative of u. That's my favorite way to say it, because you get to say f and u a lot. I don't know why I like that. Another way, oops, hold on, crashed. It's like the sensors heard me say that. Another really common way of saying it, which is basically the same as this one. I view these as equivalent. dy dx, the rate of change of y with respect to x is dy du times du dx. You will use this all the time. It's a very flexible version of the chain rule, and you'll see, we're gonna do problems. What's really interesting is that it appears as if this is kind of working as fractions work. So let me see, what can I do here? So we got this, and then this, and then this like random thing here, right? So if you start off with dy like in the top, and you end with dx in the bottom, and everything else is the same on diagonals, the chain rule will work. It's pretty magical that way. So do I dare try to highlight this one that way? I don't know. Here to here. Wow, I lost it there for a second. And then dx is here. Dx is here. Now, everything in between, you got du and a du. You got, what colors can I use here? This and this. And then you got, I don't know, this, that's a dark highlighter, and this. As long as the diagonals are the same, you end up with like the first top thing and then the bottom last thing, the last bottom thing, whatever. This is an incredible way to think of the chain rule, and it'll serve you really well. Another weird thing is the units will almost always work out when you're doing this. Like you could almost just look at the units of the functions involved and kind of like multiply them in such a way that it gives you the units you desire, and that will work. But again, that's for the future. So these things are various forms of the chain rule. We're going to use them. I'm going to come back in the next video and actually maybe do some things. So is there more to this? No, I'm looking, sorry. On my other computer, I have the wrong set of notes up, so that's great. All right, I will see you in the next video.